Hello everyone, welcome to Digital Image Processing class. In this video, we will introduce how to enhance image contrast using histogram equalization. Histogram represents a pixel intensity distribution of an input image. As you can see on the screen, the distribution of pixels in a low contrast image is in a dense region. To enhance the image contrast by fully utilizing the entire intensity range in the spectrum, we can adjust the pixel intensity distribution so that all pixels are equally distributed in the histogram as an uniform distribution. This process is called histogram equalization, which usually increases the global contrast of images and allows the enhancement of areas with lower local contrast. Before we describe the process of histogram equalization, please allow me to introduce the concept of cumulative histogram. This is because cumulative histogram plays an important role in the histogram equalization process. As shown on the left of the screen, in an ordinary image histogram, we count the frequency, that is, the number of pixels for each intensity level. A cumulative histogram is a type of histogram which counts the cumulative number of pixels in all of the bins up to the specified bin. For instances, bin 1 in the cumulative histogram holds the pixel count of bin 1 in the ordinary histogram. Bin 2 in the cumulative histogram holds the pixel count of bin 1 plus bin 2 in the ordinary histogram. Bin 3 in the cumulative histogram holds the pixel count of bin 1 plus bin 2 plus bin 3 in the ordinary histogram. Similarly, the last bin in the cumulative histogram holds the pixel count of all bins in the ordinary histogram. To obtain a cumulative histogram count in MATLAB, we can simply use QSUM function. Assume the variable h represents a 5-bin histogram count. We can obtain the cumulative count for h by applying the QSUM function on h. The QSUM function will return a vector of 5 elements as shown on the screen, where the first element is the same as the first element in h. The second element is the sum of the first 2 elements in h. As you can see, the third element is the sum of the first 3 elements in h. Similarly, the last element is the sum of all elements in h. As aforementioned, equalized histogram counts can be considered as a uniform distribution, so that the entire pixel intensity spectrum can be fully utilized to enhance image contrast. In an ordinary image histogram, a uniform distribution is represented as the red line shown in the plot on the left. In a cumulative histogram, a uniform distribution is represented as the blue line as shown in the plot at the middle. Here is another example of histogram equalization. As you can see, the tire image on the upper left corner is a grade level image with a relatively low contrast due to a lot of pixels are in the low intensity levels. To evenly redistribute the pixels in the dense areas, we're spreading the pixel equally in the entire spectrum as shown on the right, which results in the high contrast image as shown on the upper right of the screen. As you can see on the screen, in the top row, the plot on the left and in the middle represent the ordinary image histogram and the cumulative histogram of the image on the right, respectively. At the bottom row, the plot on the left and in the middle represent the ordinary image histogram and the cumulative histogram of the image on the right, respectively. The histogram equalization can be achieved with the following process to redistribute pixels. For a pixel intensity in the original image, as shown in step 1, we find the corresponding frequency in the cumulative histogram of the original image as shown in step 2. According to the frequency previously found, we look up the same frequency in the cumulative histogram of the enhanced image and map the frequency count to a new intensity level as shown in step 3 and step 4, respectively. It is worth noticing that the cumulative histogram of the enhanced image should be a cumulative histogram of a uniform distribution, which should be aligned with the slope. Therefore, based on this assumption, we can simply obtain a line equation to represent the cumulative histogram. This process enables us to map any pixel intensity in the original image to a new pixel intensity in a contrast-enhanced image. In MATLAB, we can apply a HistEQ function on an image to obtain an enhanced image using histogram equalization approach. Here is an example code to demonstrate how to use HistEQ function in MATLAB. As previously mentioned, the histogram equalization usually increases the global contrast of images. However, histogram equalization often produces unrealistic effects in photographs. To overcome this disadvantage of histogram equalization, contrast-limited adaptive histogram equalization (CLAHE) is introduced. In the case of contrast-limited adaptive histogram equalization, the contrast limiting procedure is applied to each neighborhood from which a transformation function is derived. CLAHE is developed to prevent the over-amplification of noise and obtain a better enhancement result. Here is an example code to demonstrate how to use contrast-limited adaptive histogram equalization in MATLAB by applying a depth-hist-EQ function on a grade-level image. In this example, you will see we compare the results obtained from the histogram equalization and from the contrast-limited adaptive histogram equalization side by side. Here is the comparison of results obtained from the previous example code aforementioned. On the left of the screen is the original tire image. The image in the middle is the result using the histogram equalization approach. The image on the right is the result of contrast-limited adaptive histogram equalization. As you can see, the contrast-limited adaptive histogram equalization approach gives you a better enhancement comparing to the histogram equalization.